Okay, let me begin straight away with, first of all today I want to do Kruskal's algorithm for finding a minimum spanning tree. So if you've done discrete maths at school you probably know about this already. We finished a lecture yesterday with a spanning tree of this particular graph. That spanning tree came about because we were looking at shortest paths starting at the vertex here. We found shortest paths using Dijkstra's algorithm to every other vertex. And that gives a tree, essentially a breadth first search sort of tree. And we calculated by adding the weights of each edge that the total number of weights was 41. The question is, how do you find a spanning tree? That means a subgraph that's a tree that covers every vertex. So a tree with, in this case, 12 vertices. How do you find one with least possible weight? That means the sum of all the edges. There'll be 11 edges. We want this to be as small as possible. And I claim there is such a tree, in fact, with weight 34. And there's a well-known, very easy way of doing this. It's called Kruskal. Well, there are several ways, but the easiest is called, the most natural is called Kruskal's algorithm. And I want to do that first of all today. It's pretty straightforward. So this was actually introduced, I think, at the same year possibly as Dijkstra's algorithm. So the object is to find a minimum spanning tree in a connected graph in which every edge has a positive weight assigned to it. And let me just remind you of the definitions. So, first of all, a spanning tree, that simply means that we're looking at a collection of edges inside the graph that allows us to connect all the vertices without cycles. So it's a subgraph that is a tree, because there are no cycles, and the tree, remember, is a connected graph with no cycles. So it has to connect all the vertices, not just cover all the vertices, it has to connect them all together, and there must be no cycles. So all the vertices of G are included, and typically some of the edges. Obviously, if you start with a tree, you finish with a tree, but typically you'll have to remove some edges. And in fact, if there are n vertices, we know that a tree has n minus 1 edges. That's the spanning tree. But that can be done for any graph, as we did with the searches. We had the DFS tree, the BFS tree, but now we're putting weights. We're assigning weights or lengths to each edge. So we can then, given a tree, a spanning tree, we can add up all the weights or lengths and see what that number is. And if you can find, well, there will obviously be such a spanning tree for which that sum is least. That's obvious. You just list all the spanning trees and find one or more that have the minimum value of total weight. I've written the total weight as sigma d because, remember, I used the symbol d for the weight assigned to each edge, say between vertex I and vertex j, assuming that I and j, that these two vertices are adjacent. Assuming that this forms an edge, you can talk about the weight of that edge, because we're talking about that's what a weighted graph allows us to define. So we want the sum of all the weights in the tree, not the sum of all the weights in the graph, that will be constant, but the sum taken over all the edges of the tree to be least. That's what you might call a minimum spanning tree, or MST. Now, a minimum spanning tree may not be unique. There may be several. You can easily concoct examples by just having all the weights equal. There may be several minimum spanning trees, but by its very definition, you can't change the minimum sum because the sum is minimal. If you find another tree with a lesser sum, then that will be the minimum spanning tree. So always remember that the sum, when you have a minimum spanning tree, this sum, that will be fixed. You can't find two minimum spanning trees with different sums by definition of the concept. Let me go back to the diagram. Okay, we did this yesterday. So we started with a graph with lots of green edges. The process of finding shortest paths, which you can forget about for the moment today, produced a tree consisting of the red edges. Okay, all the red edges form a tree because there are no cycles amongst the red edges, and all the vertices are connected to each other. So the red edges form a tree, connected graph with no cycles. But the red edges, so all the edges in this graph, you can't see it anymore, but they all had weights, they all had numbers assigned to them. Okay, here are the numbers assigned to some of the edges. When you add all those numbers up in the tree, that's the numbers associated to the red edges, you get a number which in this case was 41. Okay? The question is, can I find a different spanning tree, so a different collection of red edges that form a tree, for which the sum of the weights is less than 41? So you might say, well, look, I've been a bit, probably I should have chosen, I should have chosen more edges here with smaller weights rather than choosing an edge with weight 8 there or 9 there. That's a silly thing to do if I want to minimize the length, the sum of the weights. But you have to do it in such a way that you can reach all the vertices. In fact, there is at least one solution with 34. That's the solution. If you look at that, that's a tree. The red edges form a tree still because you can reach all the vertices. There are no cycles. And if you add up the weights, let's actually do it for this example. I'm going to construct this, show you how to construct it. But if we add up the weights on the red edges, we get 5 plus 4 plus 7 plus 1. That's a good one to put in. This is 3. This is 3 again. 2, that's another good edge to put in because it has a small weight. 2, again, good. 1, excellent. 3, and it seems another 3. So I need 11 if it's a tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the sum is 16, 17, 20, 25, 27, 30, 36. Is that right? Thought it was 34. 9, 2 8s are 16, 17, 20, 25, 28, that's my mistake. 28 and 6 is 34. Okay, so that tree has total weight. We could say that for the tree, the sum over the red edges of the weights of each edge, denoted D, so here D is 2, for example, is equal to 34. And that is, in fact, the lowest sum you can get for this particular weighted graph. Okay? So how do you get that? How did I construct this? This was constructed with Kruskal's algorithm. And it's much easier than Dijkstra's algorithm. It's completely straightforward. So let me tell you now how the algorithm works. So here's the algorithm. Very simple. It's just explained in the box. I'm not going to prove why this works. It's actually harder to prove why it works than Dijkstra's algorithm. But this is all you do. You want to construct the edges of this tree. So we've got, remember the diagram, we want to find the red edges. The whole idea is these instructions will help us to find the red edges forming the tree. That eventually, when you have them all in, will form the minimum spanning tree. And you do it step by step. You start with nothing, as you often do in mathematics, And then you choose one by one the edges of least weight. Okay, and I put joint here because someone asked me last time, what happens if two are the same? Doesn't matter, you choose any one. But you choose you keep choosing an edge of least possible weight. If there are two of the same least weight, you choose one of them in either order. Both are going to be chosen, probably not necessarily, because you only choose these edges and keep them if you don't get a cycle. As soon as you get a cycle, that's no good. You haven't got a tree, so you can't add an edge if it forms a cycle. That's the only proviso, and you keep going until you have a spanning tree. Or another way of saying that is you keep going until you have n minus 1 edges, assuming that the number of vertices is n. That's all there is to Kruskal's algorithm. So I'll do it now. I'll do it with the example. Actually, it's understanding quite why you get a spanning tree. There are some subtleties here which I'm afraid I haven't really gone into. But it's not very difficult. This process will succeed. You will be able to connect all the vertices in a connected tree. What is not at all obvious is the fact that the total weight, the sum of the weights, will in fact be minimal, taken over all such spanning trees. That's not at all obvious because this algorithm seems to do the obvious thing step by step. It takes the least possible edge, the least possible weight, one by one. It's not completely obvious that's going to give you overall the sum being as small as possible. In fact, it's quite tricky to prove that. It's an idea. It's one of these greedy algorithms in which it does what appears to be the obvious thing at each individual stage, but that's a sort of local operation. It's not clear that when you put it all together, you get the correct answer, but you do. Okay, so let me just, there are a couple of questions on the sheet about this. Well, you can construct lots of examples yourself. Any weighted graph you can play with and find a minimum spanning tree. So all the questions relating to Dijkstra's algorithm, they're weighted graphs. You can also find minimum spanning trees for those. Can I remove this? So here's the same graph, blank, apart from the weights. Let's add on the red edges. Let's apply Kruskal's algorithm. So here, it's probably worth idea. It's a good idea to sort of have a small table to remind you what edges you're adding and their weights. So let me try and do that. Well, there were two weights, you remember, of weight 1, so they're far apart, so we won't get a cycle with only two edges. So we add both these edges of weight 1. Okay, those are the only two edges, I think, in this graph of weight 1. So those are added immediately. So we've got a 1 and a 1 we've added. And then we look to check we don't have any other 1s anywhere. Please check yourself. Now we look for edges of weight 2. And we can add them in any order. As I said before, if they're joint least, we can add them in any order, as long as we don't get a cycle. So we can start with that one on the left. We can add this one here. No problem there. Are there any other 2s? I don't think so. So we've added a couple of 2s. What we have now, is that a tree, what we have now? The red edges, do they form a tree? No, because it's not connected. The tree has to be connected and no cycles. So a tree has to be connected. And with no cycles. Well, certainly there are no cycles, that's okay. It's not a tree, it's a forest. It's called a forest. Collection of a graph, each of whose component is a tree, is called a forest. So this is a forest, that's why I called it F. Okay, you construct and you keep growing this forest until it all comes together. So it actually has 3 trees, rather simple trees, but that consists of 3 trees. And then we're on to weight 3. This is a bit more tricky because there are lots of them. So here's one, weight 3. Here's another. Can I put this one in here? There's another one here. That's okay. No cycles. I can spot another one here. But I have my solution here to check I'm not making a mistake. And those are all the threes, I think. So I have added 4. 1, 2, 3, 4 of weight 3. No other threes? No. Okay. So we go on to the 4s. Well, there's one here that's not going to be problematic because it's isolated. Other 4s. Well, there's one here. Yeah, I can't put this one in. If I put this one in, it gives me a cycle. 1, 2, 3, 4. It gives me a 4 cycle. 1, 2, 3, 4. No, 5. Is it 5 cycles? I'm not very good at counting cycles. 1, 2, 3, 4. It's a 5 cycle. But anyway, it's a cycle. So that edge can't be put in. Okay, so this can't be added. Can't be added because it gives a cycle. Don't care what sort of cycle. Okay, is that clear? So we just discard that, we forget about that, and we see if there are any other 4s left, which I don't think there are, so I think I only added 1 4. Now we look at the 5s, and there's one here is completely unproblematic, and there's one more, there are 2 more 5s. Now I can't add this, where are we? I can't add this one here, this one, because that would give me a 1, 2, 3, 4, 5 cycle. And I can't add that one either, because that would probably give me another 1, 2, 3, 4, 5, 6 cycle. But anyway, it gives me another cycle. So neither of these can be added. So no more 5s can be added. So I added 1 5, didn't I? Now we're on to 6. Fortunately, these are integer weights, so the weights don't have to be integers. I can't add this one, that would give me a triangle, that would give me a 3 cycle. So this is not allowed, this can't be added. Are there any other 6s? No. So we're on to 7, so I didn't add any 6s. We're on to 7. Now, this is not on, so I can certainly add this 7 here because that just connects this stuff to the main part of the graph, of my red bit. So now everything's looking pretty connected. Is that the lot now? So I've added a 7. And how many things have I added? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's finished. That must be a tree. Because there are 11 edges, it has to, and there are no cycles, it has to be a tree that spans all the vertices. So that is a minimum spanning, well, that is according to Kruskal's algorithm, the red edges give you a minimum spanning tree, according to Kruskal, and it does. And the total weight is 2, 4, 6, 9, 12, 15, 18, 22, 27, 34. There may be, I'm not claiming this is the only minimum spanning tree. I sort of guess it is in this particular graph, but I'm not certain. And that's identical to the picture I showed you before.